that. What is the idea of penetrance? Does anyone, what does that mean? Basically, it's the idea of like how prevalent, the way I think about it, this is not the exact definition, but is how prevalent is the disease in the population. So something can be a dominant, it can be like a dominant mutation, but it can still have very low penetrance. So it's kind of weird to think about. On the flip side, you got something with that's recessive, but it could have high penetrance, where it can still be, what's that, you have a question?
Is it for population or for an individual?
I believe it's for populations, because it's talking, I could be wrong, but I wrote something, I wrote it down.
It probably makes more sense for
I think for population, because it's saying overall, because here's the thing, with dominant recessive, that's more of like the Mendelian thing that we've always thought about. So if something's dominant, what does that mean? If I've got big A, little a, I'm going to get whatever the big A phenotype is, right? Recessive means I got to have little a to get whatever that phenotype is. So that's talking about like an individual basis or how mechanistically this thing is going to operate. However, on a population-wide thing, penetrance becomes a bigger deal. So let me use the example of BRCA, BRCA1, right? What happens if you have mutated BRCA1? What does that usually lead to? It can lead to breast cancer, right? Is BRCA1 dominant or recessive on the mechanism? So if I get one mutated BRCA1 allele, I have mutations to it? No. How many mutations do I have to have for BRCA1 to get basically the defective version? I gotta have 2. So I have to have little b to get that. So in terms of the mechanistic definition, is BRCA dominant or recessive? It's recessive. However, I'm sure Blaine talked about this, overall it acts in a, I don't really understand how he kind of switches, goes from recessive and dominant, but the BRCA will have, in my opinion, it's like a high penetrance. And so here's sort of the idea of how I think about it. You must have 2 mutations in order to get the screwed up BRCA. And what is BRCA important for? Anyone remember? Well, yeah. But what does the protein do?
No, recombination repair?
It helps basically with DNA repair, strain invasion, exactly. Let's go back to the second example. So, but once again, sort of like Huntington's disease, there's often, is there a genetic sort of component to breast cancer, or does it run in families basically?
Yes.
Yes, and the reason for that is, so if I am born and I have big B, I have to have how many mutations occurring to get the screw up in BRCA? I have to have it happening twice. I have to have 2 random mutations, both occurring in the same exact gene. An allele, one allele on the one chromosome, and the same allele on the other chromosome. That still happens, but it's typically very, very rare. However, what happens if I'm born with big B, little b? One of my alleles is already screwed up, right? Now how many mutations do I have to get to then get the screwed up BRCA? Just 1. So that's what Blank is talking about when he says, in terms of the mechanism, how we think of Mendelian genetics, BRCA is recessive. I must have little b to get it. However, when we talk about it with breast cancer very often, what happens is that people are often born with a big B, little b already. And once I have that, I just need this one to go to then get the, the disease. So, and I think the way Blank is talking about it is that this is something by a mechanism, it is recessive in terms of I must have little b. However, it usually has very high penetrance because if I'm born with big B, little b, I only have to lose one other of the big B's to then get the screw up in BRCA. And then typically, once I have the screw up in BRCA, do I have breast cancer?
Not necessarily.
No. Because once again, what is BRCA important for? DNA repair. As soon as I lose BRCA, what then happens? I'm much more likely then, when I have other issues and mutations in the DNA, I can't fix them because I don't have this recombination repair. And therefore then, we then see those effects. So we use some other examples too. I would know every disease in this lecture and the next one, know the disease, and know whatever it is we're talking about that's going to be important for it. If you have osteogenesis imperfecta, this is a dominant disease. And he's going to use, basically for this, he uses examples of dominant versus recessive, not in terms of, like, it's still based on the definition of big A and little a, but he's trying to give it more of like a sort of why on a function level of the protein, why these are the way they are. So in this disease, osteogenesis imperfecta, what's screwed up? Collagen, right? You guys done collagen yet in biochem?
Yeah.
Collagen is a long polymer, right, of a bunch of, and whatever the individual thing of collagen is, it's all stacked up on each other. So in this case, let's say someone has big A, little a. Each of these different, this is basically chromosome 1 maternal, chromosome 1 paternal. Both of these, here's the different ones, chromosome 1, whatever chromosome it is. Within here, right here is where I'm going to have the collagen gene, all right? And so they get transcribed and made into the collagen component that gets added to this long collagen polymer. Both these are getting transcribed, and then so when I'm making collagen, I'm basically taking those subunits from both the protein made from this one and the protein made from this one, from this chromosome 1 and this chromosome 1, paternal and maternal, all right? However, everything that comes, this is my screwed up one, everything that comes from here is going to be not the proper actual protein, the proper actual thing that needs to get added, right? So as soon as I make this and I add it to my long chain, I screw up everything downstream where that's going to occur. This is why this disease is going to be dominant. Because I'm basically making a long polymer from individual subunits, but my source of half of those subunits is screwed up. Half of the subunits are coming from the one that had the little a, the bad allele, or the big A, I guess in this case, because it's going to be dominant. The big A had the screwed up one, little a is the good one. Big A over here, every time I make a subunit, it's not the proper form, proper structure. So as soon as I add it onto that, that whole polymer of collagen, the collagen molecule is screwed up because both these are going to be required to make that long polymer of collagen. Yeah, there's a very small chance maybe some collagens are only come from this one right here, but typically we're going to transcribe both of these. They're then going to make the subunits, and those subunits, when they come together, as soon as I add the bad one, it screws up the whole collagen molecule. And therefore, that's why it acts in a dominant fashion. Compare this with phenylketonuria, PKU. In this case, the gene is going to code for the enzyme, the protein. The enzyme functions on its own. I don't combine this enzyme with this enzyme. So once again, I've got my good one and my bad one. My good one makes the enzyme. Can this enzyme do its job? Yes. This one makes the same enzyme, well, it's different due to mutations. This enzyme can't function properly. However, this enzyme doesn't interact with this enzyme. They're both supposed to be for the. They're both going to be an enzyme. However, I don't need to have these combined to have the proper function. So all of my good enzymes can actually make and do their proper function. The bad ones can't. Because I still have, hopefully, a high amount or normal amount of this good one over here, I won't have the disease. Or maybe I'll only get the disease when I go into certain metabolic states where I have to have a higher amount of this enzyme. But in most cases, we're going to assume we're going to have usually enough for this. That's why this is a recessive disease, because I can screw up half of the protein that's made, but this half can function on its own just fine. This half can't, this half's okay, therefore the disease, there's no effect of the disease on me because I still have some good version of the enzyme. In the osteogenesis one, I make good and bad, but these have to get combined into a long structure, so all of the structures are fucked. All right? So that's the way we sort of think about it as we go forward. So once again, we have this, where he's talking about is it dominant or recessive, and on the exam, or if you are able to go to Blank's Q&A, I think he has only one more Q&A, right? I think the one's today. I'm probably going to do the other Q&A, but you guys can just ask me any other time too, so you don't have to come to that. But the idea here, once again, on a mechanistic standpoint, I must have little b, so it's recessive in that regards. However, it usually has a very high penetrance because if you are born with big B, little b, there's a very good chance that big B will get mutated. So think about it that way, is that no matter whether you have big B, little b, or big B, usually throughout your lifetime in the breast tissue, you're going to get one of those mutated. That's just sort of what the average is. So if you're already born with one of them already screwed up, it's a very good chance you'll probably lose the other one throughout your lifetime and then develop. And in that case, then leads to a high probability of developing breast cancer. But if you're born with the big one and big one, I don't care if I lose one. I still have the other good one that's going to be fine. Once again, Mendelian inheritance recombination, where things are going to recombine during prophase 1, and it leads to new sort of variability that we're going to see, and bring it back to haplotypes. A haplotype block means that everything in there, not always, but for our purposes for now, no recombination occurs within here, but on the ends of the block, that's where we have those recombination hotspots, where things are going to recombine very, very quickly. Not very quickly, but at a very high frequency. So you're going to have this right here. I have two haplotype blocks within between them. That's where the recombination hotspot is going to be. So when I'm making I'm making sperm. When I'm making sperm, almost all my sperm are still going to have everything that I have in here is always going to travel together. I'm going to make that gamete, and therefore, but there's not. I don't know. I have no way of knowing if what's in here travels with this, right? All haplotype blocks travel independent of other haplotype blocks. So even though right now I've got two blocks right here, when I'm making my gametes, I can tell you, or I can be almost certain, everything in here is going to be in the same sperm together. Everything in here will be in the same sperm together, but I have no idea if this and this will be in the same sperm together. And that's the whole idea of what's going on here, right? I'm a lot of sperm today. So, next thing. This, once again, is the haplotype block. In this case, what's in these squares right here, those are the VNTRs, the variable number tandem repeats. Excuse me. They are going, once again, because it's a haplotype block, these are always going to travel together with this big D allele. All right? So, in an entire population, this is one block. However, a different block could also have a big D, but here it could have maybe 3, 4, 6. They're variable. It's not just you have one for the big D, one for the little d. You have a whole bunch of haplotype blocks within the population. All right? But for every block, I know, if I know that this is a 2 right here, I can basically then for sure know this one has to be 3, this one has to be the big D allele, this one has to be this, has to be that. So once again, what's the point of doing this? Why do we care about setting things up this way? Yeah, define them and really to study the diseases that we want to be looking at. So in the beginning, here's what we did. Let's say there's some disease that runs in this family. Everyone in this family, or most people in this family, have this disease. But I have no idea, I don't know anything about genes, basically, or I don't really know what all the genes are. And I have no idea of knowing, like, basically, I don't know that this is the actual disease gene. That's what we're saying we don't understand. We don't know this yet. So what we do is, I set up a pedigree, I look at the family history, and from there, I then need to look for what do all of the people in this family that have this disease have in common on the genetic level. It's very hard to go through and look at every gene and sequence every gene and do it that way. So instead, what's much easier to work with? The VNTRs and the SNPs. Because we do know where all of those are and we have a database for all of those. And that's exactly what's going on here. So let's say this is the D disease. Where if you have big D, you have the disease. Because I think the shaded means you're affected, right? I think, right? Yeah, so everyone with the shaded is going to be affected. No, that they're not going to be affected. Keep in mind, which one's male and female? I don't remember. Square is what, male?
Yeah.
All right, so just keep that in mind in case Blaine throws a little curveball. I don't know if you ever mentioned that. So just be comfortable with that. And basically, what they did is, I see anyone that has the shaded in shape, they have the disease. Step 1. All right. Step 2 then, I want to look at all of their DNA and see what do they all have in common. If we already knew what the disease was and the gene was, it'd be very easy. I can look at their gene in the DNA. But I don't know that yet. So what do we use then to help identify or use as markers is I use the haplotype blocks. Because it's much easier to identify SNPs and VNTRs than it is to look at normal and disease alleles for the gene. And that's exactly what we're doing. Because this is one haplotype block. What does that mean? It always travels together. So what that means is, if I can say, oh, in this block they have a 2 and a 3 at the first VNTR and the second VNTR, I can then assume I know what the allele is going to be there. Because these always travel together throughout populations, throughout the parents into the offspring. That's exactly what they did. So in the beginning, anywhere you see a D, it was basically a question mark. We had no idea. And what you do is, once you see who all the disease patients are, you get all their DNA, and throughout the genome, I want to look at, all right, let's see what all these have in common. Basically, I'm asking, which haplotype blocks do all of the diseased people have that none of the healthy people have? And when you do that, looking for the VNTRs, I saw that in one unique haplotype, everyone had 2 repeats for the first one, 3 for the second one, 1 and 4 throughout that block. Whereas this normal patient, did they have any of the disease? They didn't have the disease, and they do not have anything within that block. So that's the first way. That's how we do it from the beginning. I say, okay, look, here's what they all have in common. They all have this one haplotype block. The reason we can use blocks is, once again, everything within that block always travels together. So that's what we're looking at here, and we see, okay, if they have these in here, I know then something in there is causing the disease. That's what it tells me. So once I identify the block, then I say, what are all of the genes located in that block? So I go to the human genome browser, and I look at, I input it in, and I say, within this region of the DNA, what are all the potential, or what are all the genes in there? I then get a list of all those genes, and then I say, okay, based on what I know about those genes, which of them, if they're screwed up, would lead to a disease state like this? Hopefully it's just one, and then we can sort of go from there. But if it's more than one, we then need to sequence each of those genes individually. However, how many genes do we have total? Over 20,000, right? So you can't start, you can if you wanted to, it would take you a really long time and you'd waste a lot of money starting at the beginning and sequencing the gene, all 20,000 genes for each of these patients. That's a waste on so many levels. Instead, what do? We narrow down the number of genes I want to sequence and look at. How? By using these blocks. Does this make sense? This is like if you understand this, the rest of the lecture should hopefully come pretty easy to us. Does this make sense for the most part for everyone? All right, cool. Once again, we're doing it with VNTRs. We could also do it with SNPs. So how many SNPs are there in the human genome? You guys remember? 3.1 million, I believe. So that's another number I'd probably be pretty comfortable with. So that's the number of SNPs I have. And once again, SNPs are different from person to person. However, all of the SNPs within this one unique block are going to always travel together. And whatever alleles are in there will always travel together as well. This picture again, we're looking at now all of the haplotype blocks. Now, like I said before, I've been talking to make it more simplistic where we say, if you have a block, there is never recombination within there. That's not true. You still can and often do get recombination within a block, but it's much, much rarer than obviously at those recombination hotspots. So on this example, we found one person has the disease. However, they are missing the full block, where we don't see the actual 8, 3, so once again, these are all VNTRs within there, but I don't see the 2, 7, and 10 down there. This actually is even better for us, because let's say I have one block, and we know this is where the disease is, because everyone has this block, and let's say there's 5 genes in there. Can I be certain for sure from this point which of those genes is the one that's leading to the disease? No. I have an idea it's one of those 5. I can do more research into it, but I can't tell just from this exactly which one of those genes is the one that's screwed up. However, what happened in this last patient over here? There was a recombination within this haplotype block, which once again can happen, but it's not as common. And that recombination basically occurred right here, where they still had the 8, 3, and 8, but then right here, this one chromosome combined with the other one when they made the gametes, and then they had this other thing in here that actually isn't part of the block. However, Does this patient number 4 still have the disease?
Yeah.
So now that tells me, I know for sure it's a gene